Hello, I'm Alan Denton from Physics Partners, and in this short film we're going to look at how to teach gas laws and particle theory. The film is part of a series to help you with your physics teaching, especially if you're new to teaching, new to physics, or just looking for some new ideas. I'll focus on ways to introduce this concept that may help avoid misconceptions, and some ideas that may help if you are teaching remotely. Feel free to pause and take notes, or rewind and watch again. One of the main aims for this topic is for students to be able to relate what is going on at a microscopic level, where students should be visualising hundreds, if not billions, of atoms bouncing around, colliding into each other, to the macroscopic properties of that gas, including the pressure exerted on any container walls, the absolute temperature of that gas, and the volume it's taking up. To help with this, let's start by looking at a simple model of how gases can exert a force. So my mental image of why we get a pressure exerted by a gas is by visualizing lots and lots of molecules, lots of atoms, all bouncing around inside some kind of fixed container. So here I've got a tray and the particles are bouncing around and colliding into the walls. Why do we get a pressure exerted on that wall? Well, because each time an atom collides with that wall, it bounces off. And if you've got enough atoms over enough time, then you end up with a constant pressure being exerted on the side of that container. We should actually try to be honest about what are some of the problems with our model that we just showed to people. Firstly, in our model it was only two-dimensional, whereas of course in the real world it is three-dimensional. In our model we only saw particles moving with a very similar speed, whereas in the real world they're going to be going at a wide range of speeds from very slow to incredibly fast, with the average speed probably around 500 meters per second, around 1,000 miles per hour. In our model the atoms were big relative to the spaces between them, whereas actually they should be tiny compared to the spaces between them. And finally, our atoms slowed down whenever they collided into something, whereas we should assume that the particles bouncing in a real gas are actually colliding elastically. That means no energy is lost. This starts to give us a relationship between pressure and force. So we can see that if we are having lots of collisions hitting the wall, then over time the overall force acting over a fixed area will give us a pressure. And normally the units we use for this might be newtons per meter squared. So what factors can affect the pressure exerted by the gas? Well, the first one is if there are more collisions. So because either there are more particles or because they're moving faster. By having more collisions, there will be a bigger force exerted over every area. But equally, if particles are moving faster, then each collision will be bigger. And so because there will be a bigger change of momentum when an atom hits the side wall, there will also be a bigger force exerted from that. What follows is a thought experiment that can be really helpful for students to make the link between the particle movement and the bulk properties of that gas, like pressure. When I do it with students, I get them to put their answers on mini whiteboards for me. So with that in mind, let's see if you can do a thought experiment with me. First of all, let's picture the pressure exerted by 10 particles all bouncing around at a particular average speed. What I want you to do is I want you to figure out what do you think will happen if those particles, the same number of particles, say the same number of particles, but they're in half the volume. What will happen if you've got the same number of particles, but you've got twice the volume? So what will happen to the pressure exerted on the walls of these containers in that situation? What about if you've got twice the number of particles, but you've got the same volume? And then the hardest one here is what will happen if you've got the same number of particles in the same volume, but they're going twice as fast. Okay, so pause the video, have a think what will happen to the pressure in each of these four situations. Okay, so I'm going to draw the situations now and then we'll discuss what's happened to the pressure afterwards. Fantastic. Okay, have the diagrams helped at all? If you weren't sure before, have a look at the diagrams now, pause the video again and see if it's any clearer. Okay, so what have we got? Well, here we've got the same number of particles but in half the volume. What does that mean to the pressure? Well, if we consider each wall, there's twice the chance of a collision because there are 2 times the number of particles in there. So we've got half the volume, which means we've got twice the pressure. Similarly here, we've got half the pressure exerted, half the number of collisions. So if we consider a box here, we've only got on average 5 particles there. So compared to what's going on here, we've got twice the volume and we've got half the pressure. Down here, we've got, actually it's the same situation as this. On average, we've got twice as many collisions happening on each wall. So this is a relationship between N and P. So we've got twice the number of particles, we've got twice the pressure. And our final one here is the relationship between the velocity they're moving at. Now this is the hardest one. I said it was the hardest one. So if we've got twice the velocity, then we've got twice as many collisions and we've got twice the force exerted by each of those collisions. So we actually end up with 4 times the pressure. Now if we put all of that together, that gives us an overall relationship. So it says pressure is inversely proportional to the volume. So pressure is inversely proportional to the volume, or pressure times volume is equal to some constant. And that's one of the rules that our students need to know. This one tells us that the pressure is proportional to the number of particles. That comes up at Key Stage 5, both physics and chemistry. This one's a little bit harder to understand, but if we've got twice the velocity squared is proportional to the pressure. And if you happen to know that velocity squared is also proportional to the absolute temperature, that is the temperature measured in Kelvin, then you can say that pressure is proportional to the temperature. So we've got 3 results. PhET have got a wonderful simulation, and in it you can vary all of the different properties. So here I am increasing N, I'm adding more particles into the mix. You can vary the volume and see how that's going to affect the pressure as well. You can do other things like increase the temperature, but just be careful, as all of these variables affect the pressure, you might break the vessel. And there the lid you can see popping off. One really nice demonstration about the relationship between pressure and volume is to get a syringe and put some marshmallows in the end. As long as the end is sealed, when you increase the volume, you will see the marshmallows grow. And that is because the pressure is decreasing inside the syringe and the pressure of air inside the marshmallows is making them grow. This can also work well with a wine bottle with marshmallows inside and a vacuum van. So we can investigate conceptual understanding with concept cartoons like this one, or we can look at mathematical equations by doing some problems like this one from AQA, where you've got a pressure gauge and a gas tube, you increase the pressure and you see how the volume changes over time. The way to solve this begins with the understanding that PV equals a constant, and I think it's always helpful to say then P1 V1 is equal to P2 V2. So whatever the pressure initially was times the initial volume is equal to pressure 2 times the volume 2. And here's the rest of the solution sped up for you. Here's a summary of some of the main points that we've been talking about today. And just a quick reminder that temperatures should be measured in an absolute scale, that is from absolute zero, so probably using Kelvin. I hope that's been a help in your teaching. Hope to see you again soon.